Yeah. Okay. So,
And just make it.
yes, please. Yeah.
So, if you have a credit for parent, or if you have indicated that you want parent support, I have sent the form here, so this and providing the document.
Yeah. Okay. So, so let us look at this function again, the one loop integral which generates the imaginary part for the equal mass bubble. So this is represented by this in the book of Golovich, Holstein, and Donoghue, Golovich, Holstein. And it has an integral representation, dx logarithm of 1 minus a x times 1 minus x. This is actually the same as our friend, the j bar of s. And if you have 16 pi squared, so this is sigma of s. This I wrote yesterday also. So this is sigma of s minus 1 divided by sigma of s plus 1, like this, plus 2. This you can check, where sigma of s is the space factor. It arises 1 minus 4m squared by s. So earlier today, when I did the thing from Ramon, that was done in the Euclidean. So it had showed up with a plus sign. But this, if you do with Minkowski, then it comes out all right. So this, the imaginary part of j bar of s, tell me, this thing over here is a logarithm. So what is the imaginary part that it is supposed to pick up? Yeah. Why don't you all come to the front? I mean, easier for me also to have an audience. Yeah. So just look at this and tell me where the imaginary part of the j bar of s is coming from when s is greater than 4m squared. When s is greater than 4m squared, then this particular thing picks up a minus sign, right? So the logarithm of a negative whatever is, so what is the imaginary part of a log of a negative number? So it's just I pi, right? So the imaginary part of this j bar of s, of course, it have the sigma of s. So it will be 1 by 16 pi. The I pi, the I and the pi are gone. So the 16 pi squared, one of the pi's goes away. You have 1 by 16 pi times sigma of s, theta of s minus 4n squared. And you can check for yourself that this function itself obeys a dispersion relation. So j bar of s itself obeys a dispersion relation. And now you can tell me where it is analytic in this S plane. Because of this logarithm, it obviously has a branch point over here at 4m squared and it's got a cut over here. Okay. Otherwise, it's a perfectly well-defined function, etc., etc. And you can study this thing a little bit, and you can also show to yourself that it is real analytic. You can look at the value of the function just above the cut, below the cut. You can see that the imaginary parts, apart from a sign, are the same. All the nice properties that we talked about yesterday are reflected in this thing. Okay, it is a real analytic function. It has this straightforward branch point, etc. And if all that is true, then obviously it has to respect a dispersion relation. A dispersion relation that of course needs to converge. And in this case, we'll do a subtraction at 0, and then it suffices to have one subtraction, and then it will converge if you write it like this, 4n squared to infinity m of j bar of s, which is the straightforward thing, divided by s prime times s prime minus s ds pi. Okay, it's a very straightforward thing, but it's worth doing just to fix all the ideas for yourself. Okay, but my friend here, she had studied this bubble of Smirnov, which had a simpler structure, right? It had one mass and the other one was massless, and it was just a log. So you can do the dispersion relation for that function, and you'll see how straightforward it is. Okay, it'll be just a dq squared by q squared, q prime squared by. Okay, so I can just tell you. So there may be some minor mistakes, but So this is an m and this is m equal to 0. And we said that it must be a log of 1 minus q squared by m squared, right? So the imaginary part of this, imaginary part, let me call this some f of q squared. So imaginary part of f of q squared will be I pi times theta of q squared minus m squared. Nothing else. So then if you do an integral of 1 by pi from m squared to infinity, d q prime squared by q prime squared minus q squared. If you do this integral, what is the integral that you get? It's a logarithm, right? dy by y minus x. So if you do this, you will immediately get back logarithm of 1 minus q squared by m squared. So these are all minor exercises that you can do to fix these ideas for yourselves. And yesterday what we did was this exercise of looking at the scalar form factor, and then we were trying to derive some results for it. And we said that this scalar form factor, you don't really have to know what is a scalar form factor, except to say that it is some quantity that is of interest to us, which has a representation like this. So this is the source which couples to a pi-pi pair, and this is a scalar and transforms as a scalar, which means that this will couple only to a j equals 0, I equals 0 state. And then you can write at one loop. So this is a tree and this is equal to 1. So at one loop, you get that this thing is going to do this, and then it's going to scatter like this. And then there's an imaginary part associated with cutting this thing. And then we can see what this is. And we wrote down the answer that it is 1 plus s by 16 pi squared f pi squared L4 bar minus 1 plus 2s minus m pi squared by 2 f pi squared times j bar of s. And this j bar of s here produced the imaginary part that we needed. And one of my friends who's here, she helped us come and derive this thing. Although I said that you needed this I equals 1, j equals 0 state, which means it was a partial wave f00 of s. We wrote down this amplitude and lo and behold, it worked. Why is that? So we have to discuss a little bit more. What is the relationship between the amplitudes and the partial waves, okay? We didn't say that yesterday. In order to do that, we need to do the kinematics a little bit more. Before I do that, I also want to say a little bit about the electromagnetic form factor. The electromagnetic form factor. Magnetic form factor, which has 1 plus various polynomial pieces plus logs in m pi squared by mu squared, etc., plus 1 by 96 pi squared times q squared minus m pi squared times h of q squared by m pi squared. So this is the same j bar that shows up over here. And then the analogous exercise that you're supposed to do for the electromagnetic form factor is that it's supposed to be something like this that produces an E plus E minus pair like this with this photon coupling over here. And it couples to the channel j equals 1, I equals 1. Okay. So from the pi-pi scattering amplitude, I have to be able to pull out a factor like this and establish that unitarity is respected by this particular observable. Okay. So yesterday I wrote down for you the pi-pi scattering amplitude schematically. This was a pi A, pi B, and pi C, pi D, P1, P2, P3, P4, pi C like this. And we said that S over here was P1 plus P2 squared, and this was P equals P1 plus P3 squared. And then there's a U channel, which is P1 plus P4 squared. And the kinematics of this process in the center of mass frame center of mass frame. S is the square of the energy. We also need an angle in scattering, right? We always need an angle. And it turns out that for equal mass scattering, it's straightforward. Now this pi is one of the most beautiful systems because it has a lot of symmetry, it has equal masses, it has very nice symmetry properties, and there's no other process which has such beautiful properties. Any other property, for instance, pi k to pi k scattering, in the T channel, it is a different process. It's pi k to pi k in the S channel becomes pi to kk bar in the T channel. It's much more complicated. And the masses are unequal, and you don't have a straightforward relationship between cosine theta and STU, and it's just a mess. Okay. So we don't care about that because we are only going to talk about equal mass scattering. So cosine theta S, as it is called, happens to be T minus U divided by 4qs squared, where qs squared is this quantity S minus 4 m pi squared divided by 4. It also shows up over here. It's the same Q that shows up over here. It's the same combination that shows up in this J bar of S. It's always this 1 minus 4 m squared by S because this is Q squared, which is the square of the momentum transfer, of the 3 momentum transfer. So that is the reason why it looks like this. Okay. Now comes a lot of little bit of kinematics that people often learn in their coursework, but we have to do this in order to make contact with various observables pertaining to the pion scattering system, also quantities that show up in dispersion relations, and also quantities that are computed in effective field theories, such as chiral perturbation theory, and also what the lattice people do and what they try to measure on the lattice. Is everybody with me? Is somebody with me? Is anybody with me? Besides myself, no. Of course, I make very good company, but still, I'd rather some of you are also with. Okay, so this I had already introduced yesterday. We have this partial wave expansion that I mentioned yesterday, where in the context of pi scattering, we take the amplitudes of definite isospin in the S channel, which are functions of STU, ST and U, as mentioned over there, and we introduce the partial wave expansion 2L plus 1 times Ti with an L. Sorry about this handwriting. Different books use different notation, and I get mixed up between all of them, times PL of cosine theta S. So this is called the isospin definite isospin in the S channel. This is the partial wave amplitude, and this is the Legendre polynomial. So another way of writing the same thing, T minus U by this is also equal to 1 plus 2T divided by S minus 4 m pi squared. Okay. So this is cosine theta C. So in the physical region, you will all agree that S is always greater than 4 m pi squared. Who in this room does not agree that the physical region corresponds to S is greater than 4 m squared? Does anybody agree or disagree? Everybody disagrees. Obviously, the energy has to be more than 4 m squared, otherwise you will not have particle production, right? So this thing is positive, and cosine theta in the real world has to lie between what and what? -1 and +1, right? Cosine theta for physical scattering. So if this thing is positive and it's 1 plus something, what does it say about t? It says that t has to be negative, it cannot exceed. Otherwise, this whole thing will be positive, and then you'll get cosine theta to exceed 1, which will not be physical. Okay. Nevertheless, later we will see that it's possible to extend analyticity in the cosine theta plane to beyond the physical region, but that's not physically accessible. All right. So in the physical world, S is always real and greater than 4m squared for a scattering problem, and t has to be less than 0. Otherwise, cosine theta will exceed 1. So what are these Legendre polynomials? PL are these Legendre polynomials. Give me some examples. What about P0 of Z? Can somebody tell me what is P0 of Z? Where -1 less than or equal to Z less than or equal to 1 is equal to 1. Then P1 of Z is Z. P2 of Z is equal to 1/2 of 3Z squared minus 1. So as you can see, L determines the highest power of Z. Okay. So P3 of Z is half of 5Z cubed minus 3Z. It also has alternating parity and all these wonderful things. So this is either odd, odd, this is even, even. And we also have the very important orthogonality property -1 to 1, that PL of Z, PL prime of Z, dz over -1 to 1 is equal to 2 by 2L plus 1. Sometimes we only take the integral between 0 and 1. Even then, this thing will have to work, but this is the standard normalization. And L equal to 0 is called the it's called the S wave. What is L equal to 1? This is P wave. And L equal to 2 is called the D wave. And L equals 3 is called the F wave. After that, it's called G wave, etc. Okay. But this is a very important property because it allows me to get the partial wave amplitude from the total amplitude. How do I do that? I multiply both sides by the Legendre polynomial of the partial wave that I want, and then do the integral. And because of the orthogonality, this thing here will drop out, and then when I project this onto the partial wave, I get the partial wave that I need. So yesterday we also wrote down some examples of these things. We wrote down delta AB, delta CD, A of STU, delta AC, delta BD, A of TUS, plus delta AD, delta BC, A of UST. And we also said that we can write down amplitudes of definite isospin in the S channel with the 3AS plus AT. I'm using an abbreviated notation now. T1 is AT minus AU, and T2 is AT plus AU. And then we said the pi0 amplitude was wonderful. It was just AS plus AT plus AU, totally symmetric under the interchange of ST and U and various swaps. Okay. Now, what tells you that you had to find amplitudes of definite isospin in the S channel? Somebody else may have said, I'd rather do it in the T channel. And his enemy would say that I'd like to do it in the U channel. Okay. So it's possible to do all of them. And it's possible to start with one of them and cross to the other channel also. So if you wanted to do it in the T channel, then you use swaps. It would have been 3AT plus AS plus SU, etc. So there's a bunch of matrices that allow you to go from amplitudes of definite isospin in the S channel to amplitudes of definite isospin in the T channel. And what name shall we give the matrix? that allows you to cross from one channel to another. Let's think of a name. The English Channel, you cross from France to England. So if you want to cross from the S channel to T channel, what do you need? You don't need the channel and you don't need the train, but you need crossing matrices. Crossing matrices. And what shall we call them? I want to call them C to cross from the S to the T channel. And you can find out what the entries of these things are. And the entry of this is 1 by 3, 1, 5 by 6, 1 by 3, half, minus 5 by 6, and 1 by 3, minus half, and 1 by 6. Supposing you wanted to cross from the S to the U channel, there would be a corresponding SU channel. And if you wanted to cross from the T to the U channel, it's called a CTU. Now, all these you can actually explicitly construct from this kind of algebra, but it has to be, it has to respect the selection rules of angular momentum algebra, because the SU2 isospin algebra is exactly the same of SU2 of rotations. And it's the same Wigner 6J symbols and 9J symbols that are used to generate all this. And the book of Burckhardt has a very beautiful description of how to get this. Okay. So this has been studied by all kinds of people, but anyway. And what we did yesterday was to study this example where we started out with ASTU at leading order in current algebra. And we said that this is S minus M pi squared by F pi squared. Okay. And from this, we constructed T0 of STU, which one of my friends did for me yesterday, and wrote it down as 2S minus M pi squared by F pi squared. And this thing here was also sitting in the unitarity relation for the scalar form factor, if you will remember. But this is the amplitude. But from this over here, I need to produce the partial wave. This is only the amplitude. How do I get the partial wave for this? And I need to project it on to the L equals 0 partial wave. The 0 partial wave corresponds to P0 equal to 1. Therefore, since this thing here is only a linear piece, it has no dependence on cosine theta. Cosine theta is Z, right? Z is 1 plus, it is T minus U by this. There is no T minus U dependence over here. That is why this is F00. It has no cosine theta dependence. Therefore, in this Legendre basis, the amplitude itself is the partial wave. Now, isn't that nice? Are you people following what I'm saying? I'm not saying anything very great. Okay, so that was as far as this partial wave is concerned. So F00 is just this, but there's a 1 by 32 pi times T0. Okay. There's an overall normalization factor. Now, for the electromagnetic form factor, I needed to compute the T equals 1 P wave, L equals 1. So let us construct T1 of STU. Any volunteers? We're going to look at this blackboard over here. AT minus AU. You have to construct from this. Lofty is going to tell me what it is. It's just T minus M pi squared minus U minus M pi squared divided by F pi squared, right? After all, I'm supposed to take AT minus AU. Yeah. So this is all it is. And this is T minus U by F pi squared. Okay. But I don't like T minus U as it stands. I would rather it has this divided by 4qs squared. So I multiply upstairs and downstairs by 4qs squared. So that is S minus 4 M pi squared times T minus U by S minus 4 M pi squared divided by F pi squared. Now, do you identify this thing? What is this T minus U by S minus 4 M pi squared? This is cosine theta. So it is nothing but the first Legendre polynomial of cosine theta. And if it's only the first Legendre polynomial of the cosine theta, then it means that this T1 constructed out of the chiral amplitude has only one partial wave, and that partial wave is the P wave. Okay. So we isolate this, and this is now 4qs squared by f pi squared is my F11. And that's the reason why in that unitarity relation for the electromagnetic form factor, this enters. So this enters the unitarity relation for the electromagnetic form factor. But let me also do a little bit of work, having found this T00, etc. I want to evaluate this at threshold. What is meant by threshold? This thing over here. What is the definition of threshold for the particle production over here? S equals 4m pi squared. That's the threshold. So if I plug it into this, what do I get? I get 8 minus 7. So that will give me 7m pi squared divided by 32 pi f pi squared. And this is a very important prediction due to Weinberg, and this thing is called the scattering amplitude A00, and this was given by Weinberg, very important prediction, Weinberg. Why is this called A00? Because after the partial wave expansion, one introduces something known as a threshold expansion. Threshold expansion when when S is greater than 4m pi squared. And it is introduced in the following way. The real part of FIL of S is Q to the 2L times AIL plus Q squared BIL plus etc. So in your quantum mechanics courses, you must have seen this threshold expansion, and you must have seen names given to each one of these quantities in scattering theory. The first term here is called the scattering length. The second term has a name, the second one. Has anybody heard of this? This is called the effective range. Okay, it's called the effective range. The higher terms don't have any names, higher threshold parameters. But these have the names. This is the scattering length, and this is called the effective range. So why this peculiar factor over here? This peculiar factor here physically represents the centrifugal barrier. That is, at threshold, it's only the S wave scattering that takes place. And at the lowest, at very low energies, just above threshold, is the lowest waves that dominate the scattering. If there was no S wave allowed due to various selection rules, then it would be the P wave that dominates because of the centrifugal barrier. Okay. So given these expressions, from these we can get not just A00, but you can also get the effective range B00 also, and B00 also I can get for you is m pi squared by 4 pi f pi squared. I am going to leave it as an exercise for you to do the corresponding prediction for the I equals 2 channel. The I equals 1 channel has only one prediction at this order, A11, and that is the P wave scattering length is 1 by 24 pi f pi squared. So these were some of the dramatic predictions of current algebra long before the strong interactions had been solved. Just from the properties of the strong interaction Hamiltonian and the symmetry properties, these predictions were made by Weinberg. Today, we know that this is really the low energy effective theory, and then there are corrections that we have to compute to these quantities because of the presence of loops and so on and so forth. And this is a real amplitude. There is no there is no imaginary part. The imaginary part arises when you compute loops with this model. But then this particular model of current algebra, chiral symmetries, is not a renormalizable model. So there's a whole technology to deal with such non-renormalizable low energy effective theories. You have to add further counter terms and reabsorb all these things and so on. Okay. So, yeah.
Here, on the here it goes. The leading term that word scattering, not even scattering.
Where? This one.
Yeah.
Yeah.
That's the word scattering.
It depends on various, there are different terminologies. In yes.
We know that the dimension of way has current
Yeah.
Yeah.
Yeah, that may be in the case of non-relativistic scattering. Yeah. No, this is the scattering length. This is the golden prediction of current algebra and chiral perturbation theory, and it's always referred to as the scattering length. Yeah. Now this length is so we're arguing about the definition of length. What dimensions is carrying? Yeah. Which one? This one. Could be. That could be. It may depend on the particular subfield where it is being considered. But in this business, this is always known as the scattering length. Okay. Yeah. That's in the form factor case. Yeah. That's in the case of form factors. Yeah. So in the case of form factors, this kind of expansion, the first the first leading term is called the radius, square of the radius, and then the shape parameters. Again, it is motivated, like yesterday we were discussing with Antoine, that it has to do with the Fourier transform of the charge distribution coming from the non-relativistic idea that if you have this kind of an expansion of the Fourier transform and then you look at the Taylor series expansion, then it has the dimensions of a square of a length. That's why it's called a radius in case of the electromagnetic form factor. So the curious thing about this amplitude is it is so simple, so straightforward. There are no higher waves. There are only S waves and a P wave, nothing more. There are no imaginary parts. But still, we can use this and then try to predict what the ASTU may look like if you are able to invent dispersion relations using the imaginary parts generated by this thing through unitarity. So the next step is to be able to use unitarity to predict what the imaginary part should be at the one loop level. So that's the next thing that we do. And this persists to two loop level also. And after that, all hell breaks loose. But definitely at the level of one loop and two loops, the unitarity argument persists. And then what we have is that we can have a prediction at one loop for the imaginary part of F00 of S is sigma of S divided by 1024 pi squared F pi squared. Don't be scared by this 1024. It is just 32 squared. So this is 2S minus m pi squared squared. Now again, yesterday we wrote down the unitarity relation for partial waves, the Argand circle and all those things. So there we said that the imaginary part will be equal to the square of the real part. Okay, that's the reason why the same 2s minus m pi squared that my friend calculated yesterday keeps appearing over here through the unitarity relation, and this phase space factor, which captures the onset of the imaginary part divided by this 1024 squared. Okay, so this is the same unitarity relation that we had yesterday, but this is a kind of iterative unitarity that is used over here. Then imaginary part of f11 of s is again sigma of s times s minus 4m pi squared divided by 9216 pi squared f pi squared. Okay, so then imaginary part of f20 of s is sigma of s times the same 1024 pi squared f pi squared times s minus 2m pi squared. So with these imaginary parts, if you asked, how can I get an amplitude which may be what the one loop amplitude looks like, it's possible to write this down. Just like I said that with the imaginary part of the j bar of s, you could get the j bar of s. With the imaginary part of your bubble, you could get the full bubble by just writing a dispersion relation. You may say, perhaps you can predict what the structure of ASTU would be at one loop, knowing these imaginary parts. Okay, so the answer is yes. So we have three functions, W0, W1, and W2, whose imaginary parts will be related to these. There are some factors, and then there'll be an ASTU is stitched out of this, out of these imaginary parts. Suitable dispersion relations have to be written for these three functions called W0, W1, and W2. And then from this, we produce an amplitude that looks like this, W0 of S plus 3 by 2 S minus U, W1 of T plus 3 by 2 S minus T, W1 of U. Now we know that this ASTU has to be invariant under a swap of T and U. That is why it looks like this, plus 1/2 of W2 of T plus W2 of U minus 2 by 3 W2 of S. It all looks very mysterious, but all these factors of 1 by 3, 3 by 2, all these things are actually closely related to the same bunch of Wigner 3J symbols and 9J symbols. And all these things is like fun algebra, and that is how you get this. Why do we have this S minus U and S minus T over here? Because this is the corresponding cosine theta in that channel for scattering. Okay. These over here at this order is related to things like this T minus U, but with suitable swaps. This is an example of, so where these three W0 of S, I can also write this, contains 3 by 32 pi, 2 by F pi to the 4, S minus 1/2 squared, J bar of S, W1 of S contains 1 by 576 pi, F pi squared, no, F pi to the 4th, sorry, S minus 4, I put M pi equal to 1. And W2 of S contains 1 by 64 pi, F pi to the 4, S minus 2, J bar of S. Now, this gives the impression that writing dispersion relations for something like a scattering amplitude is very straightforward. But this takes into account the fact that there are only imaginary parts of the three lowest partial waves. But we know that in nature, all partial waves are present, okay? So how do you write dispersion relations that don't just involve the imaginary parts? I mean, they may be expressed, but it doesn't mean that they are absent. And yesterday, we wrote down dispersion relations for the form factor. We said it has beautiful properties. It is analytic everywhere except in the cut plane. And then we said, upper half plane, lower half plane, all these things. It was very easy to do that because the form factor is a function only of one variable, okay? So you can use Cauchy's theorem, Schwarz reflection principle, all these things, and write down a dispersion relation. Of course, Cauchy's theorem is not going to predict where the singularities are, but we have used physical arguments to say that there are no singularities of this, that it is analytic, and therefore you could write a dispersion relation for a form factor, which is very straightforward. But here, these amplitudes are functions of two variables. So how on earth do you start writing dispersion relations for something that is a function of two variables? Okay. There is no analog of Cauchy's theorem for functions of two variables. In fact, the whole theory of functions of complex variables is very complicated. There is nothing that is very straightforward that you can just straight away apply like you did with Cauchy's theorem for functions of a single variable. So then you can be very clever and say that I'll hold one of them fixed and then write a dispersion relation for the other one. Now remember that u is not independent, okay, because s plus t plus u is always 4 pi squared. So this is not just a maths problem, but it's a physical problem where we can use these physical constraints and then try to make some sense out of trying to write a dispersion relation for these functions. The best way to try to do them is for this entire set of isospin amplitudes, because we will be able to cross from one channel to another. If you said that you wanted to write one for this just ASTU, then you don't know how to go from one channel to another with all these horrible isospin structures sitting around. So what we do is we try to write a dispersion relation for this entire set of isospin amplitudes at the same time, because we know how to go from one channel to the other, and we have to go from the imaginary part of one of these sets in one of the channels, then it'll allow you to find the imaginary parts of these amplitudes elsewhere in the complex plane. That is to say that for these amplitudes, you don't just have a right-hand cut going from m pi squared to infinity. There are other cuts also in the complex S plane at fixed t, because there may be other imaginary parts that show up, which was not the case for the form factor. Have I managed to confuse you thoroughly? Do you want me to repeat what I said, or do you want me to write a cartoon like I did yesterday between the tadpole and the bubble? Those of you who were here yesterday will remember in this part of the blackboard, I drew a cartoon or wrote a cartoon on how to think about the tadpole and how to think correspondingly about the bubble. So you want a cartoon? You want me to write that? All that I've been saying in words, do you want me to write it? Give me a yes or a no answer, quick. Okay, who said yes? Oh, you did, I didn't ask you. But anyway, so we had the form factor f of t, had very nice properties. It is in the cut plane, nothing else. Here it is complex, has both real and imaginary parts. Okay, and then forget about subtractions for the moment, and then you said that f of t was 1 by pi integral 4m squared to infinity dt prime, imaginary part of f of t prime, divided by t prime minus t. Okay. Well, if you want a subtraction, I can give you that also. F of 0 plus, make this a t and make this a t prime, like so. Okay. Fine. Now, what do we do for scattering amplitudes? Scattering amplitudes. This is the complex S plane. Let us fix t, okay? Fix t. And such dispersion relations will be called fixed t dispersion relations, okay? Fixed t dispersion relation, okay? As you can see, this subject can drive anybody insane. So fixed t, of course, I may have been insane to start with. But this also has a cut, very nice. It starts at 4m squared to infinity, okay? But the problem is, it also has a cut elsewhere, because in the scattering process that we had, this is the S channel, but there is a corresponding U channel process, which also generates a cut, because it's the same analytic function that describes scattering in the S channel, the T channel, and the U channel in suitable physical configuration. Okay, so an amplitude that is describing a physical scattering process in the S channel, you have to do some things to it and analytically continue it elsewhere, where it will be a physical process in the U channel, and there it will lead to actual scattering. Now, all these are theorems that have been proved in quantum field theory rigorously. For the form factor, everything was straightforward because it was rather simple, and the best place to read about all this is the book of Barton. The corresponding dispersion relations, there's a long history for their development. It was probably first studied by Gell-Mann, Kohlberger, and Thirring. And so this is dispersion relations, and also Weimermann, Irmer, and Taylor. But the crossing property rigorously proved amazing. I think this also probably Bogolyubov and Shirkov. Crossing property in quantum field theory, by which you may loosely say it's the LZ formalism, was proved by Bro, Epstein, and Glaser. So this is Henri Epstein. There is a lecture of his on YouTube, which he gave like 1 or 2 years ago. I think he's based in Paris, probably in his 90s, still very sharp. He even had a paper in PhysDevD about 3 or 4 years ago. Okay? So doing physics can be good for health. Not always, but sometimes, provided you've not been driven insane. Okay, so then it turns out, so there is a cut in this plane, the complex S plane at fixed T, that starts over here, and this is called the right-hand cut. That is coming from the absorptive part of the S channel, or the imaginary part of the S channel scattering itself. But we just argued that because of this crossing property, there's also an imaginary part that is generated from the U channel. And where do you think that should appear? If the S channel appears on the left, then the droite et la gauche, right? So there has to be another channel, which is, say, pour les gauchistes, say, pour les droitistes. So this is the left-hand cut, and this comes from the U channel. But in the case of this pion-pion scattering with all this good stuff, we know how to cross from one channel to another using these marvelous crossing matrices. Okay, that's the amazing thing. And I'll give you an example of an unsubtracted dispersion relation. Actually, it doesn't converge, but to justify and to give some substance to everything that I've been saying over here, I'll say that it is possible to write down a dispersion relation collectively for all the amplitudes of definitizer spin in S, T, and U that looks as the follows. 1 by pi. Of course, there must be a 1 by pi. And then there's an integral. And where shall I take the integral from? Take the integral from, obviously, 4 to infinity. And there's an energy integral ds prime over what? Imaginary part of this bunch of amplitudes, which I will now denote with a T But I'll put an I prime over here and an S prime comma T, because I'll be integrating over this variable S prime, because S prime is now the variable over here. So this is actually the S prime plane. Okay, so this is the S prime plane. Now you see here, I'm trying to do it in analogy to this. So you see the analogy over here. So here is a cut. We are doing an integral over the cut, imaginary part of f of t prime divided by a Cauchy kernel. This is a Cauchy kernel over here. So we need a Cauchy kernel there also. But this is only one function, whereas there it is a bunch of three isospin amplitudes, which are organized as a vector. Okay, so this is a vector over here, t0, t1, t2. Okay, so it should involve the imaginary parts of t0, t1, t2. That is why it has this index I prime over here, times delta I prime. All three of them, there may be a summation over more than one, divided by S prime minus S. Okay, so this accounts for the right-hand cut. Are you all with me? Unlike the form factor, which had only one cut, everything was straightforward. There was only one function, very straightforward, nothing but Cauchy's theorem. Here life is a bit more complicated because there are three amplitudes at the same time, but the principle is the same. You need an imaginary part, you need a Cauchy kernel that you have written down over here. So this has accounted for the right-hand cut. But life here is more complicated. There, this was wonderful, very simple. Barton says you don't have to do anything more. Whereas here, nobody is telling us anything. And we are saying that, look, there is this other right-hand cut also. So how do I go to this right-hand cut? I have to go use the crossing matrix to go to the U channel, CSU. And then I have the I prime divided by, now this is S prime minus U, where U, of course, is, so but U, of course, is 4 minus S minus T. Okay. So this cut here doesn't start at 4m pi squared, but it starts, depending on the value of S that you have over here, this cut is going to move around. And it is determined by the combination 4 minus S minus T at a fixed S at a fixed T. Remember, T is fixed. So here, the dispersion relations, when you write them down, they are not manifestly crossing symmetric. You can't go to the T channel and all these things. You have broken the manifest crossing symmetry by singling out T, and you're writing down a dispersion relation at fixed T. And this therefore means that this is the best that we can do, because rigorously, this is all you can prove as far as these dispersion relations are concerned. Now, this is of course too good to be true. And we also have to write down where this thing converges. This converges for minus 28 less than T less than 4. This is amazing because this thing even converges outside the physical region. Okay, so that's a nice thing. I said earlier that physically T has to be less than 0, but you're able to go a little beyond T equal to 0. And this is all based on work that was done by Harry Lehmann, a great pioneer in these things, and extended a great deal by André Martin, another very important figure in this field. He fortunately passed away during this COVID business. So this is rigorously true. And there is something else that I had already argued that it's not possible to have a simultaneous dispersion relation in more than one variable. However, Mandelstam introduced something which has never been proved, but a plausible dispersion relation in two variables for pion scattering, also for pi nucleon. There's something known as the Mandelstam variable, Mandelstam representation, which says that minus 32 less than T less than 4, this converges. However, this integral itself may not converge, right? Because for this integral to converge, this imaginary part has to die off fast enough at very high energies. And for the moment, we don't have any handle on how fast this thing is going to die off at large energies. Would it be nice if you had some kind of a handle on how fast this thing would die out? If you look at the topics that I have promised in these lectures, you'll get an idea. Have a look on the Indigo page. Yeah. You can do it. It's all allowed. I mean, after all, there's symmetry. This is one representation. You could do that. Yeah. In some other world, some other Shayantan may be doing that. But he had better get the same answers as you. Yeah. So what are the topics that is proposed in this analyticity business? It's so small. Are you able to read it? Yeah. What are the terms you've seen?
Fireman scattering, bomb factor analysis, Roy equation for pipeline of scattering.
Okay.
Froissart.
Oh, Froissart bound, Marcel Froissart. This French guys here will get very upset if you don't say this name's correct. Froissart bound. So this Froissart bound is another thing that tomorrow we will try to prove, because we already have a roadmap for tomorrow. And for the moment, if I assume that the Froissart bound is true, then for pi scattering, this thing will converge if there are two subtractions. You don't need more than two subtractions. Okay. So let us try to write a version of these dispersion relations, assuming the validity of the Froissart bound. Okay. So let us assume the validity. So this actually does not converge because im S prime T of S prime T does not fall off fast enough. However, the Froissart bound says this is Marcel Froissart bound says that two subtractions suffice. See here, I introduced a subtraction over here, a subtraction. And the price for the subtraction was that I got a factor of t over here, and I got a factor of t prime sitting over here. Okay. So if I subtracted this one more time, I would get a t squared over here and a t prime squared inside the integral. Okay. So this is how you make integrals converge, by subtracting them. But this was again a very simple example. It's far more complicated for scattering amplitudes, because there's a bunch of them, but I will pick one particularly useful way of writing this, and write this of Ti of St is, this time my friend, the crossing matrix CST shows up. Remember, this is at fixed T. If this is at fixed T, then the subtraction constant, this is called a subtraction constant. So here it will not be a subtraction constant, but it will be a t-dependent constant, because I'm doing it at fixed t. All right. So this thing, I'll call it a bunch of subtraction constants, alpha I prime of t. So that is the leading unknown t-dependent function, which does not have an S prime dependence or an S or U dependence. And then there will be one more term, which will again involve a column vector b I prime, unknown bunch of subtraction constants b I prime of t, and then this has to be multiplied by S minus U. Okay. It has to be, because I have done two subtractions because of this. So this thing here had no dependence on t. The next, if I had subtracted this one more time, then I would have ended up with something that depends on t in this case. So analogously, I end up with one of the variables in which I am trying to do the dispersion relation show up. And because of the properties of the interchange under S, P, U, all these things, it is the combination S minus U. Okay. And then it's exactly the same as before, 1 by pi integral 4 to infinity dx by x squared this time instead of s prime squared times delta I prime s squared by x minus s plus c su I prime u squared by x minus u m ti prime of x comma t. So this is a form of the doubly subtracted dispersion relation that we should try and use. The only problem now is we don't know what are these unknown t-dependent functions. This is alpha over here and this beta over here. We don't know what these functions are. That's because we have not related it to any physical process so far. We have only been doing mathematics so far. If we try to put in some physics, maybe we can eliminate this thing and we will end up with item 3 on your wish list. On your wish list, we have already done form factor, at least I think so, and we have done pi scattering. Have we? Have we done pi scattering? I don't hear you. Yes, okay. And this Roy equation, which is what we will do in this hour, and tomorrow will be the Frossard-Baum. Okay, and that will be the end of the topics that I have proposed that we do. Now we take a break. Yes. Yeah.
Comment further on the nature of it, but the right-hand side is square root and the left-hand side is also square root.
I don't know. I can't immediately say.
So
Yeah.
actually, the technical theory can have this parameter still represent this pattern, they use that.
Yeah.
And you do actually lower it.
Yes.
Each case, of course, actually lower side, you have amplitudes which are complex and other elastic. And
Okay, so let me continue a little bit, but me make some comments. One of the things you people should have asked me was how is it that only for I equals 0 and 2, I had an S wave, but for I equals 1, I had a P wave. Okay, this is a question that you should have asked me, but you didn't. So I'm going to ask the question, why is that the case? So it's actually very straightforward, because if you remember, the T1 was written as AT minus AU. Okay, and then the Legendre polynomial is T minus U by S minus 4. So the combination T1 picks up a minus sign under the interchange of T and U, and the Legendre polynomial also of odd weight picks up a minus sign under the interchange of T and U. Okay, so this is called generalized Bohr statistics, that the I equals 0 and 2 have only the S wave, the D wave, L equals 4, L equals 6, L equals 8, whereas the I equals 1 channel will have the P wave, will have the F wave, and L equals 5, 7, 9, etc. Okay, so this is a good thing, an important thing to keep in mind. But now I'm going to do a simplified version and not look at all these isospin amplitudes, because it was a real mess carrying around those crossing matrices, etc., etc. So I have a very nice, useful laboratory where I can do some work without worrying about all these crossing matrices, because there's one particular amplitude which has beautiful symmetry under the interchange of S, T, and U. And what was this amplitude? So let me remind you, it was pi 0 to pi 0 scattering amplitude, which actually is T0 plus 2 times T2. If you just look at the definitions, you will see that the pi 0 amplitude is fully symmetric under the exchange of S, T, and U. So to write down these dispersion relations with two subtractions that we just did before T looks very simple for the pi 0 amplitude. And let me call it T00 of STU. There is still an unknown T-dependent function, which I'll call T00 of T. Then in principle, there should be one more, but that thing vanishes because it had an odd combination of S and U, if you remember. Therefore, it is absent for pi 0 amplitude. And then we straight away jump to the dispersive part, which is an integral from 0 to infinity, ds prime by s prime squared. And because the U channel, S channel, T channel are all the same, I have a very simple way of writing a dispersion relation for this amplitude, which is s squared by s minus s plus u squared by s prime minus u, and an imaginary part of T00 s prime at fixed t. We can't escape from the fact that this is a fixed t dispersion relation. Okay, and see that this imaginary part is evaluated along the cut over here, and we don't worry about anything because this u squared, etc., is all taken care of, and we just have an integral from 4 to infinity. Okay, so this is very nice. You don't have to bother about anything else. Now I'm going to do some algebra of the kind that Padmanath's son can also do, adding and subtracting things. So even he knows that you can add and subtract T00 of 0 comma t, and let me add T00 of t comma 0. Okay, because this thing is fully symmetric, it should have been 0 t, but I can interchange this and write it as t comma 0, where I'm using the full symmetry under the exchange of S, T, and U. Let me do this one more time. T00 of ST minus T00 of 0t plus T00 of T0, which is what I have over here, minus T00 of 40. What does this mean? T00 at 40? That means that this is evaluated at threshold. Okay, S equals 4m squared at threshold. And at threshold, the only contribution to the scattering amplitude comes from the S wave scattering length, nothing else. because of the centrifugal barrier, all the other waves are killed at threshold. And the S wave just starts with the scattering amplitude plus q squared times B0, 0, etc. But q squared is 0 at threshold. So the only thing that is left behind is A0, 0. Now, isn't that nice? So A0, 0, 0. So this idea was first introduced by Bonnier and Winmau. All French people, because a lot of this activity was going on in France at that time. So Winmau is also from France somewhere. So this yields a beautiful result that we can actually get rid of the T dependence. See here that the T dependence is sitting here in the second argument over here. Okay. So when I take this minus this T dependent part is going to get killed. Similarly, the T dependent part is going to get killed by this. So that is the beauty of this particular thing. And then, of course, this thing has become algebraically more complicated, but doesn't matter. The T dependent unknown function has been eliminated, and that has now been pushed into this quantity A0, 0, 0, which is a measurable quantity. It's an experimentally accessible quantity. So this is the most amazing trick, and this gives an representation for the pi0 amplitude plus T times E minus 4 pi integral ds prime, leaving out the 2s prime minus 4, imaginary part of P0, 0 at s prime 0. So this is the forward part of the scattering amplitude divided by a denominator that has become a little more complicated, but what can we do? Can't do anything about that. Minus 4 times s prime minus 4 minus s times u divided by pi, again integral ds prime, 2s prime plus t minus 4, imaginary part P0, 0 of s prime t divided by s prime times s prime minus s prime minus u, s prime plus t minus 4. This is a very beautiful representation, and it is very useful also because now you have a representation for this pi0 amplitude entirely in terms of the imaginary part in the physical region, and a little bit of unknown stuff which is sitting in this scattering length. Okay. So this is a beautiful structure, and in the next step, when I want to do this for the set of isospin amplitudes, it's going to look more or less the same, except that there will be a bunch of these crossing matrices which makes this thing look somewhat ugly, but that we cannot help. So here there is only one unknown, which is the scattering length of the pi0 to pi0 scattering. Whereas in the case of the isospin amplitudes, there will be two unknowns. The I equals 0 scattering length and the I equals 2 scattering length. Okay. There's no other unknowns. And the rest of the dispersion integrals will look very similar, except that they will be multiplied with various entries of the crossing matrix. Okay. So this is the Bonnier-Winmau representation, and then the corresponding representation for isospin amplitudes is what was given by S.M. Roy. So that is the Roy representation for the isospin amplitudes, which is exactly the same idea. There are two recent reviews on this topic. It's kind of amazing that there are still people writing reviews on a rather old subject and people still giving lectures on this rather old subject. And as I was just talking to Raghav Krishnan, there is a context why many of these things are being discussed again for precise comparisons with the lattice or the bootstrap guys and so on. They also need to know these things inside out, do as much as possible. So there's a context for this. And it is definitely cheaper than building one more LHC. Okay. So let's keep that in mind. So there is a review by Colangelo from last year, where he has essentially looked at the same topics. Even the list of the topics that he follows is more or less what I followed, although my lectures, I gave them 2 years ago and I'm following the same script. So I guess great minds work alike. And then there's one by Kubis, Bastian Kubis. So Colangelo here, he talks about a Toy model pi cubed or lambda phi to the 4 theory, in which he does the Roy equations. It's actually the same as doing the pi 0, okay? Because there are no additional quantum numbers. So his toy model is the same as our pi 0, pi 0, pi 0, pi 0, pi 0, pi 0. He has some good discussion. There are one or two things which are a little on the technical side, so which I have not covered, especially having to do with the Lehmann-Chilean representation, which is all not needed. This Kubis is also another good review article that you can have a look at. And there's one by Zwicky from a few years ago, which is not so great because there are some inconsistencies in notation and just gets very complicated. Okay, so I'm going to write down the result coming from an analogous treatment of the isospin amplitudes. I will not go through the intermediate steps, but just give you the final answer, what the amplitude looks like. So the amplitude Ti, the set of isospin amplitudes, St, looks like this. There is a matrix G1, II prime, where II prime are the isospin indices, which involves the two S wave scattering amplitudes plus an integral from 4 to infinity, obviously, dx by x squared times a matrix G2 II prime STX times im T prime of x0. Notice that there is an im evaluated at 0, okay, the forward part. So the same kind of structure goes through over here. And then there must be a piece which involves something that looks like this, which is S prime T. So let's see what that is. G3 of I prime, STX, im of T prime X T this time. And it looks very similar, except that this G1 is a little more complicated. G1 is S times 1 plus T times CST plus U times CSU. Then this G2 is going to look similar to this. So it's minus T divided by pi times x minus 4, as it should be, I guess. I hope I'm not missing any of the terms. U CST plus S CST CSU times identity by x minus t plus CSU divided by x minus u naught, where u naught is 4 minus t. Then there is a G3, which is exactly like this, minus SU by pi times x minus u naught times 1 by x minus s plus CSU divided by x minus u. None of this is very difficult. You have to just start with this, then you have to swap the various arguments and regroup the terms and then just write it out, and then this will follow. No problem at all. Okay. You can do this in Mathematica if you're not keen on doing it with paper and pencil. So this here is called the Roy representation for the isospin amplitudes. And then what SM Roy does is he wants to project this onto partial waves. Okay, so that's the idea is, so these famous Roy equations, as they are called, is obtained Roy equations. Equations for what? Equations for pi partial waves. So the both sides are projected onto partial waves. How do you do that? Well, you multiply by the relevant Legendre polynomial, and then you integrate from -1 to 1 for cosine theta. But there's one more thing you can do, which is you can introduce a partial wave expansion for the imaginary parts also. Okay. One thing that you're doing is to project onto partial waves. The other thing is also to project these onto partial waves. See that there's an amplitude on the left-hand side and there's an amplitude on the right-hand side. So idea is to project this onto partial waves. The process, of course, means that the right-hand side also has to be multiplied by the Legendre polynomial. And then you can also give a partial wave expansion for this. So this means that there is a set of coupled equations for the partial waves. That every partial wave on the left-hand side is coupled to all partial waves on the right-hand side. Okay. And the functions that relate or couple these are known as the Roy kernels. So there are functions. So furthermore, obviously we can't do all this here. Furthermore, the imaginary part on the RHS can be expanded in partial waves. So this leads to a set of equations that couple the partial waves to one another. Partial waves to one another. But not all. On the right-hand side, you have only the imaginary part of the partial waves. Okay. So all the waves are coupled to the imaginary parts of all the other partial waves. Couple the partial waves to one another. So LHS will have real and imaginary parts. The RHS has only imaginary parts. So schematically, how should we write this? Schematically, we can write this in the following way. You can say the partial wave of a given isospin channel and a given angular momentum S as an angular momentum L as a function of S will be coupled to K I L I prime L prime imaginary part of F of I prime L prime of S prime, and then there is, so this thing here will have two arguments, S and S prime. And then there will be an integral over ds prime, like this. Okay. So these are what are called the Roy equations. So naturally, the low energy sector is completely dominated. Low energy is dominated by S&P waves. Dominated by S&P waves, which is also okay for us because anyway, the chiral expansion that we saw, chiral expansion or current algebra, we saw that only imaginary parts of S&P waves are present. So the analysis of the S&P waves at low energy is key to making this whole chiral perturbation theory more and more predictive. Okay? And they occupy a very special place, and there is experimental information available on the real and imaginary parts from various sources. So the reason why this is interesting and important is that there is experimental information available on these things. So we can get experimental information on this. From indirect sources, because there are no pion targets available. Pions are unstable particles. So they have to be obtained indirectly from, let us say, pion nucleon scattering, or the E plus E minus to pi plus pi minus, E plus E minus to pi plus pi minus. So this is a source of information on the form factor, on the electromagnetic form factor. And from the Watson theorem, or Fermi-Watson theorem, so this gives information on delta 1,1. Okay. This is what we saw yesterday. So this is an important source of experimental information. And the other delta 0,0, delta 2,0 are obtained from pi n scattering indirectly. So you have, let us say, a proton over here, and the pion comes here, and this thing is surrounded by pions, a halo of pions, and then you get pi scattering like this. So indirectly from pi n scattering, you can get information on these things. And then there is one experiment, which is the decay of a rare decay of a kaon. Rare decay of a kaon. So this is called the KL4 decay. KL4 decay, where a kaon comes in and then it produces an electron and a neutrino, and then produces two pions which then rescatter like this. So this is a pi. So there was a Brookhaven experiment from about 25 years ago, which provided a source of information on this. So Brookhaven National Lab. Then there are other sources on pion scattering lengths coming from lifetime of the pionium atom, and also some other kaon decays. So the pionium atom was an experiment at CERN called Dirac, and the kaon decays are various Na48, etc. 48, 62. Please check all these things. Okay, I'm just kind of ad-libbing over here. Because it's a kaon going into a 4-body final state. Lepton, yes. Lepton and neutrino. I mean, it cannot produce a lepton without a neutrino.
Yeah. Okay, actually, I was trying to count the number of leptons, because if I now try to count the number of leptons, there is 1, 2, and pion might decay into a muon and a muon neutrino, which means in total I will get 6, right?
No. This is a pion rescattering. This is the pion rescattering over here. So it's a pion pair and a neutrino and a lepton pair. So that's KL4.
Okay.
And then there's a rescattering of the pions.
Okay.
And from that, measurements of the angular distribution of those pions in the lepton. then they can get information.
Oh.
Okay. It's not 4 pions in the final state.
No, I was
So-
thinking 4 leptons in the final state.
No, two leptons and 2 pions.
2 pions. Yes. Yeah. Okay. Thanks.
Maybe we can just spend a minute looking at, once again, this one or two of these kernels. What do they look like? So TILOS is, so this is a slightly different notation, doesn't matter. GILS of S, sigma L prime, sigma no, this is sigma over I prime, sigma over L prime, 0 to infinity, 2L plus 1 times integral 4 to infinity, ds prime, GII prime, LL prime, SS prime, imaginary part of DI prime, L prime of S prime. And these constants, lambda 0, 0, look like A00 plus 2A00 minus 5A20 times S minus 4 by 12. Lambda 20. So I told you, it's more complicated with the isospin amplitudes, but not that much more. 2A00 minus 5A20 times S minus 4 by 24. Lambda 11 is 2A00 that's 5A20 times S minus 4 by 72. All these factors, 2, 5, all these things are entries of this crossing matrix. Now let me look at the combination for pi 0 scattering, which is the easiest for us to look at. All these are known functions. So in the pi 0 case, here 0, 0 denotes the pi 0 case. 1 by 3 A00 plus 2A20. G00 0 of S prime. Now remember that we have projected things onto partial waves and we have introduced a partial wave expansion and all that, S minus 4 by S prime minus 4, S prime minus S, minus 2 by S prime plus 2 by S minus 4 times logarithm of S minus 4 plus S prime divided by S prime. Now this log here is a very typical function when it comes to the diagonal coupling. So this is the pi 0 S wave coupling to itself, okay? The S wave coupling to itself. The S wave will couple to the S wave, the D wave, L equals 4, 6, 8, 10, etc., etc. So the leading contribution will be the self-coupling of the pi 0 partial S wave, partial wave to itself. And this is what the kernel function looks like. So it has all these nice factors and it has this logarithm, which is very important. Okay. So this thing here takes care of one of the cuts. One of them is the usual right-hand cut. And this thing here, I guess it has a left-hand cut, but I can't immediately say whether that is the case or not. There's one question that you people forgot to ask me. So I'm going to ask you that question. Remember, we started out all this with fixed T dispersion relations. Okay. So we have treated T differently. So the full crossing symmetry is not there, even though the way we wrote down the dispersion relation looked very nice. The imaginary parts all appeared very symmetrically. It was at fixed T. So this means that if you have a phenomenological amplitude, it does not yet have all the crossing symmetry. You have to restore that crossing symmetry. And in order to do that, you have to impose one more condition. So this thing is called the crossing condition. So a crossing constraint is needed. That is that T00 at ST has to be T00 at S4 minus S minus T. So this leads to a condition that T00 ST is A000 plus all this. And then okay, so I better write this 1 by pi integral ds prime k of S prime ST m T00 of S prime T. This is the same thing that I wrote earlier. I should have kept it at that time instead of erasing it. S prime 0. And there is a condition that involves this k, which is that integral 4 to infinity k of S prime ST m T00 of S prime T minus k of S prime S 4 minus S minus T m of T00 of S prime 4 minus S minus T. I have to close this bracket plus another one k of S prime 4 minus S minus T 0 minus k of S prime E0 m of E00 of S prime 0. Close this bracket, yes, is equal to 0. In this whole thing, there's a ds prime over here. This is a telegraphic introduction to all this Roy equation theory, which is not too much. The use of this in phenomenology is where the hard work is, where you introduce a phenomenological model for all these waves with parameters, and then you have to run chi-squareds to make sure that you have the best fit to data, the best fit to the theory, and so on. Okay, so this is as far as this Roy equations are concerned. So let me stop here and see if there are any questions.
Sorry.
Yeah.
In the top equation, you have written T00 S comma T equals T00
Yes.
S comma 4 minus S minus. It should be U or?
Yeah, the U is 4 minus S minus T. We know that.
I see. Okay. You are saying that T channel and U
Yeah,
channel
yeah,
are
yeah,
similar.
yeah.
I see.
Yes.
Okay. Okay. That's how you have. Okay. Fine.
Yeah,
Fine.
yeah. So that's
all clear. All clear.
that's Sayantan's friend in the alternative universe who's doing that.
No. I had a question on the below equations, but I
Yeah.
want to clear. Yeah. Thanks.
Yes.
Thanks. Yes.
I have more or less exhausted what I had planned to say today, and what I wanted to do tomorrow was as for Sabang. Okay, maybe I've gone too fast or something like that. So I think this is already a bit of an information overload. So perhaps we can stop here unless there are some urgent questions, or we can just continue in the what do you call it, the tutorial session. Is there anything that people want, discussed a little better? There's somebody who came in the morning and said wanted to ask some questions. I don't remember who it was. Maybe he's not here now. And I said, let's talk later. I don't remember. Maybe I should put on my specs, but I don't think I can remember who it was. Yeah. Is it okay to stop now a little bit? Yeah. I'm a bit tired myself. Yeah. So when would you be starting the tutorials? Start now or after some time? Okay. Okay. Right. Thank you.